So today I'll tell you the meaning of charge. There are plus and minus charges. So called positive and negative. Negative charges are the type possessed by the electrons. Just to gain your intuition. So electrons, negative. So electrons, negative. Protons, positive. And then we have neutron as well. Neutron is neutral, meaning to say there is no charge. Charges of the same sign repel one another, and charges with opposite signs attract one another. Why do they? Charge is a quantity created by human to represent or to describe particles' behavior. We create that quantity. Okay, next. This is basic as well. So if you have a cloth, you rub the cloth, and then we have another rubber rod. You can always try to induce the electrostatic force. Okay? So basically, it will attract the rubber. So we have the glass over here, and then we have the rubber. It will attract. But first things first, you need to rub the glass. Okay? So more about electrical charges. You know the electrical charge when you have your 3-pin socket? Let's say if you take any, I don't know, like a metal rod, and then you try to hold it and insert it into one of the holes, and you will get electrocuted. So intuitively, that electrocution is, it means that the charge is being transferred into your body. Okay? So, the electrification is due to the transfer of charge from one object to another. So before I proceed, I need to tell you something that particles in the universe are conserved. So meaning to say, if 10 particles are being created during the Big Bang, so until today, there will be a total of 10 particles. No? So meaning to say, let me dive into a smaller scope. Okay, when I have my balloon here, maybe I need somebody to help me to blow. Of course, I do have the electroscope, but I've discovered that the aluminum foil here is not attached to the hook, so I can't use it. I have to open it and repair my electroscope. I think you've seen this before. Of course, when I charge the balloon and then I take the balloon near to the terminal, and then the gold leaf will expand like that. So particles are conserved. So same goes to the electrons. Okay, I take the balloon, for example, and then I rub the balloon on my hair. What I'm doing is that I am not creating any extra charges. I'm not creating the electrons. But what I'm doing is I rub the balloon on my hair, produce the friction, and then that kind of friction will allow the electron to escape from my hair and then move to the balloon. So that balloon has extra negative charges. So let me try this and see if I can feel it. I cannot feel anything because the temperature here is quite humid, no? So I'm afraid it will fail because we are in Malaysia. So most of the electrons that I've induced, so I'm giving you some situation here. Even though it fails, I hope that I can successfully allow you to understand this in more detail. So if I take this, if I rub, okay, the temperature here is humid, no? So the electron that is being transferred from my hair to the balloon here will discharge throughout the water droplet in the air. I can feel some subtle attraction through my hair here, but I suppose if I try again and again to show you, I won't be able to do that. It's okay, well, that's fine. I was able to do that when I was in my office, but here it is humid, because maybe because of the existence of many humans in here, and then it produces some extra heat, even though it feels cold, but there is some small droplets in the air, okay? But you can always try this at home, but provided that your home need to have the air conditioner. Okay. So when I rub this, what I'm doing is I'm transferring the electron from my hair to the balloon. So the balloon itself will contain extra electrons. I'm just creating the friction because my movement here, my effort is actually the work done to produce the friction. And that friction is a subtle amount of heat, okay? It is a subtle amount of heat that causes the electrons to get excited and leave my hair and move towards the balloon. I hope you get the idea. You are giving the energy to the electrons on my hair and move it into the balloon. So when you bring the balloon, there is an extra negative charge. Let's say if I bring to the straw here, then the straw here will attract to it. There is a positive charge in here. Okay, when I induce, when I charge by induction, when I bring the balloon together, close together to the straw, then what I'm doing is I'm realigning the position of the positive and negative charge in the straw. I'm realigning. So maybe without the extra charges nearby, there is a uniform distribution of positive and negative charge. Uniform distribution means, for example, the male is positive, the female is negative. Let's say if I ask you to scramble around so that the probability, let's say if I select this one, so the probability of getting a male is the same as the female. Or if you don't understand it, we need to say you have the syrup drink, the red drink. It is quite famous in Malaysia. So you have to add a little bit of the syrup, red syrup, and then you have to add an extra bit of water. The water, you have to add the water, and then you have to homogenize it. So you have to homogenize it. So that homogenization, meaning to say the water particle and the syrup particles are distributed uniformly. So meaning to say the male and female should be mixed all together uniformly. For example, I'm giving you a situation. Let's say, assume that I am a model, I'm a male model, okay? I'm a handsome guy, for example, just assume that. Okay, let's assume that all of you guys are mixed together, male and female, but when I come here, so most of the women will get attracted to me, so most of you guys will come and stay close to me. So that's the idea. Okay, I'm not going to explain this because I need you to read this. This is intuitive, so I suppose if you read this, you will understand this. Moving on to the quantization of electric charges. So normally we denote electric charge in mathematics and in physics using Q. So it is either an uppercase Q or the lowercase q. Q itself, okay, listen to me, yeah? Q itself, the charge itself, is not a vector quantity, okay? It is a scalar quantity. Charge has no direction, okay? So it has no direction. But at some point, you will discover that the sign of that particular charge determines the direction of the electrical force. So it will, the sign, this is what we call the sign convention. Sign convention. When I mention about convention, it is just a human creation. It is a concept created by the physicists just to make sure that you have the right direction. I mean, the right force direction. Okay? And then here, Q is a standard symbol used for charge, okay? Electric charge exists as discrete packets, okay? Basically, it is, the charge is not continuous, okay? It is not continuous. Okay, basically, it is discrete, okay? But you cannot see the discreteness because we are at the macroscopic level. So we won't be able to see the discrete changes in the amount of charge. So what we see, because we are big, you know, we are big, so we are seeing the continuous amount of charge, but actually it is discrete. For example, if I have a pool of electrons, okay, let's say in the battery, I have a pool of electron in the battery. So as what we can see, it is just like a continuous charge, but actually it is N times E. So E is the charge of electron. Okay? E is the charge of electron. So if I'm not mistaken, if you want to access the value of E from your calculator, it should be constant 23. Okay? That is the fundamental charge. So N is the number of electrons. So let's say for that particular system, we have 3 electrons. So the total charge is given by 3 times E. So for electron, Q is negative E. For proton, Q is positive E. Okay? Both have the same magnitude. The charge of protons and electrons has the same value. So the magnitude, the modulus is E, 1.6 times 10 to the power of minus 19 coulombs. C is coulomb, okay? So again, charging by induction, you just read about that, okay? So this is what I have demonstrated to you, but instead of using the balloon, the illustration here uses the, I don't know, like a glass rod and something like that. So what it actually does is it is actually realigning the position of the positive charge and the negative charge. If you remember my example just now where the female and male are mixed together and I'm a model, I'm a handsome guy, most of the female will come and see me, come closer to me. And yeah, just remember that. So that is analogous to what is written here, okay? But again, I still haven't finished with the story. Once me, the model, the handsome guy, leave the hall, then most of you guys will get back to your respective places. So that's the idea. Meaning to say, if I remove my balloon, let's say if I charge the balloon and I bring to my electroscope near, I bring my balloon near to my electroscope, then the aluminum foil will expand like that. So when I remove the balloon, if I move the balloon away from the electroscope, then it will get back together. Okay? So before I proceed with the point charge, so I suppose that you have the same level of understanding now. But I want to address the question, why do we have charge? What is charge? Why do they attract? Why do they repel? So the reason is because we don't know what is particle, to be honest. Even if you go to the higher level, we don't know what is particle. We can only see the interaction, okay? We can only see the interaction, but we don't know what is an atom, seriously speaking. So there are many theories that describe atoms. The most basic ones are the plum pudding model. That was the unsophisticated way of doing that. But at that time, it was sophisticated. Okay? The plum pudding, the Bohr model, which is these models are useful to describe the physics at that time. But now it is still useful for education. But we have another way of doing this where the particle itself is a quantum field. Okay, the quantum field itself is just like the wave that you've learned in 103. But as we physicists, we still don't know what is a quantum field. Whether is it real physical or is it just a mathematical abstraction? We don't know. Maybe you don't understand this yet, but to be honest, I'm saying to you, it is my responsibility to tell you that we don't know how does an atom looks like. You see, an atom as a ball is just I don't know. We can only see the interaction. You are seeing me because of the interaction between particles, you see? So the photon coming from the light hits my face, and then there is an interaction with my forehead here, the atoms on my forehead, and then they interact and then bounce the photon towards your eyes. And then that photon will go inside your eyeball and getting refracted, and then it will move to there's a receptor, the photoreceptor, and it will go, the electric will go through your brain, and then you describe that as Rabi'i. We can only see the interaction. Do I look like this? I don't know. Based on your interpretation, your brain interpretation, this is me. In the actual case, I don't know how do I look like because I don't know what is atom. Okay, so these atoms, they are behaving in a way that if it is positive and it is negative, they will attract. It is just us that label them as positive and negative. That's it. Because the charge is there, but we have to label it as positive and negative. You can also create your own world by saying that instead of positive and negative, let's say alpha, beta, or maybe John and Newman. So positive and negative is just that we create that. We create that to get the same understanding that particles behave in two ways, okay? One is positive, one is negative, and then another one is neutral. So when positive meets with the negative, they will attract. Why is it that? It is because of the exchange, interaction. There is a virtual photon, so I'm not going to explain here. So there is a reason why. There is when the positive and negative meets together, even at a distance, they are actually transferring the momentum and the energy. They are exchanging the energy. But the exchange of energy leads to some sort of momentum conservation, and then so it is really complicated. But you just need to understand that there is a reason why they behave like that. As you go further and further, you become the professor of physics and try to create new theories and trying to describe what is an atom. You will never know what is an atom. That's it. Let me talk about the point charge. A point charge is a theoretical concept. It is not realistic, yeah? But the concept of charge is there, but a point charge is just a mathematical concept or a physical concept. So there is no size. Let's say if I assume that an electron as a point charge, it is legitimate for me to do that Okay, it is legitimate for me to do that. It is allowable to represent a particle with a point charge, but I need you to note that a point charge and a particle, they are not the same. Okay, they are not the same because the particle has the size, whereas a point charge doesn't have the size. So it is infinitesimally small. If you try to zoom it, so it will remain a point, zoom, 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 point. You will never see a circular, spherical, because it has no charge. Okay, yeah, this is the arrows around it are the electric field. I'm not going to cover electric field, but I'm just going to tell you that you just take a note on that. The arrows are the electric field, the representation of the electric field. So at the moment, I suppose you know that electric field do exist, but it is quite debatable whether it is really there or it is just the interaction between particles. Okay, so you just don't have to think about that. You don't have to think further. I'm just telling you the truth to make sure that all of you guys are satisfied. It's just, it is a formula. It is a formula that gives you the magnitude of the force produced by the repulsive or the attractive force. So I have a positive charge here, and then I have another positive charge here. So the force will be this way. So you imagine there is a line. That line is the shortest path that leads to one another. So meaning to say it is a line connecting between them. So I have another force. So this is proton number 1. This is proton number 2. So this is the force. The force exerted by proton number 1 towards proton number 2. So that's how we write this. So when I say F, I, J, J and I are indices. J and I are indices that indicate the different charge, right? So I have charge number 1, charge number 2. So here, I, J. So let's say if I is 1 and J is 2, meaning to say it is the force exerted by I towards J. So it is this one. Let's say if I push you, my push is given by, let's say if I am 1 and you are 2, so the force given by me to you is F1, 2. Let's say if I replace this with Rabi'i and Mizul. Mizul is a name, a Malaysian name. So force exerted by me towards Mizul. So Mizul will feel my force. So meaning to say, if I have F1, 2 is the second positive charge. So F is the force felt by charge number 2 due to charge number 1. So you have to make sure that the number that appears first is the one that causes the force. Okay? So the same goes to this one. So this is F1, 2. So based on Newton's law, of course, F1, 2 is opposite to each other because we have the positive. I mean, let's say if the magnitude of F1, 2, F sub 1, 2 is equals to the magnitude of this is 2, 1. Okay, 2, 1, F2, 1. Okay? So the formula to determine the magnitude is given by F is equals to K, which is a proportionality constant. A proportionality constant. Okay, normally we put it as KE. Q1 times Q2 divided by R squared. So R is the distance between the two particles. And then I need you to bear in mind that the formula here assumes that the two charges are static. Okay? Or even though it is not static, maybe it is within a snapshot of time. So yeah, that's the idea. It assumes that they are not moving. When they move, they create another force due to magnetic field. That will be covered by the next lecturer. Okay? But for now, you put aside the magnetic field, You put aside the magnetic field and then you think about the electric field and the electric force. So, for example, if my Q is positive, then you put the positive sign. So when my Q is negative, you have to put the negative sign. This is the convention. There is no physical reason to do that. It is just for the sign convention. So, of course, I need to add another unit vector because f is a vector, okay? So here is a scalar value. This is not a vector, so I'm not placing any arrow on top of it. So it is just the magnitude of r, the distance between the two. So I have a r cap here. So if I have 1, 2, then my r cap should be 1, 2 as well. So r cap is the, the direction. So the direction should begin from 1 to 2. So meaning to say this is r cap. That's why the unit vector here has the same direction with this one. It's just a matter of convention, just to make sure that your direction, your force direction is correct. Okay? So move on to the next slide. Okay. Again, F is the electrostatic force. I've explained this. Q1 and Q2, I've explained about R, the distance between the charges. K is the Coulomb constant. Normally you will see K itself, or sometimes I may write it as K sub E. The sub E means the electric. The electric. It means electric. So K sub E. So the value of K, listen to me, okay? Listen to me. Don't get this confused. The value of K depends on the environment. Let's say if the electrical charges are situated inside the air, then the value of K is given by this. Let's say if you have the electrical charges in a conducting materials like the metal, so it will be another value. The K itself is given by 1 over 4 pi epsilon naught. How did Mr. Coulomb derive the equation? Well, he did not derive it mathematically. What he did just, he conducted the experiment and he found that the electrical force is proportional to the product of the two charges. Okay? And then, when you do experiment, you will plot the graph like that. You measure the force, and then you also record the value of Q1 plus Q2. And then you plot here, 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 here. So basically it is proportional. But given that you fix your distance, fix the distance. So if you fix the distance, for example, you don't allow the two electrical charges to move, which is the distance between the two spheres, is constant, and then you try to increase the value of the product of Q1 and Q2, okay? And then you measure the force. So you will discover that you will see this straight line. And then he determined the slope of the gradient. He determined the gradient, which is K at that time. And then came Mr. Maxwell. He did his mathematical description, the Maxwell equation, and then that is the reason why we have the 4 pi epsilon naught. And I'm not going to derive it here because I don't know how to derive it as well. Moving forward, so you are supposed to understand the entire information here. So that's your responsibility. And then next, again, the electron, that's the value. Even though the proton has the same charge as the electron, same magnitude, same electrical charge magnitude, but the thing is, the mass of proton is way larger than the electron. But the proton has the same mass with the neutron. But the neutron itself doesn't have any charge. It's neutral. I'm not trying to say that it doesn't contain charge. If you dive into neutron, it is made up of the various flavors of up, down, charm, quark, the quarks. No? The quarks themselves have the charge. So I'm trying to give you the correct explanation. I'm not saying that the neutron doesn't contain any charge, but the entire system, the entire neutron itself, it seems like it has no charge at all. But when you zoom it and see there are subparticles, these subparticles have charge. So yeah, the symbol is n, should be n sub 0 or n to the power of 0. I don't know. Normally, I'll just state n. If you have 0 there, it's because the charge is 0. Okay? Just to indicate the charge. So apologies for my misunderstanding. Of course, the equation here is basically the same with the Newton's gravitational law, right? So if I'm not mistaken, you have learned this in 101, right? 101, am I right? So basically, it has the same meaning, but the mass doesn't have any. It doesn't have any sign convention. So mass itself is always positive. Well, it doesn't mean that they are related to each other because the guy here is due to the gravitational force. So it is better described by the general relativity. But here, even though the form of the two equations are the same, but the thing is, they are. I'm not trying to say that they are not related to each other, but they are different. Okay. But if you are trying to understand the intuition of the equation here, the electric force, so you will see the same intuition here that you use whilst understanding the gravitational force. So we can read this. If I have an opposite, a system with opposite charges, then they will attract. So meaning to say you have to, okay, let's say if this guy is negative. So this guy, I need to remove this arrow. Now they become attractive. So here to here, the force and another force. It is because, let's say Q1 is positive, because it belongs to the proton, and then Q2 is negative, so it belongs to the electron. So Q2 should have negative sign, should have a negative sign. So it leads to the production of negative sign here, okay? So the force exerted by 1 towards 2 is in reverse direction. So this is R12 is over here, right? R12, R cap 12 is this direction. But now due to the negative sign, due to Q2, you have the negative sign, so it means that the force is in backwards direction. We can have, just now I've mentioned to you about two charges. Let's say if you have a system, with multiple charges. If you look at the entire system, so you have the net force, right? So the net force is given by F equals to the summation of the combination of the interactions. Let me show you this. So remember this, F equals to the summation of Fij, where I is less than J. So this is how I denote combinations, I less than J. I'll show you the reason why. So F Ij, summation of Fij. So this is the net force, Ij, where I is less than J. Okay, where I is less than J. So let's say if I have particle number 1 and particle number 2 and particle number 3, and then I have the combination of I have a combination of R13, and then here is R23. I mean the distances R12. So I and J is the element of 1, 2, 3, and so on. So here we have 3 particles, so we have 3. So if you outline the combination, for example, 1, 2, 3, and then I have another combination, 1, 2, 3. So this is the first particle. This is the first index, I. This is your I. This is your J. So I have a combination of 1, 1, this one and this one, and then this one and this one, 1, 2, and this one and this one, 1, 3, and then this one and this one. So 2, 1, 2, 2, 2, 3, and then 3, 1, 3, 2, 3, 3. Okay. So of course, the condition here is that I must be less than J. So this one, 3 is less than 1? No, right? So you have to cancel this one, what else? This one. Yeah, you have to cancel them. Because 2 is greater than 1, 3 is greater than 1, 3 is greater than 2. Okay? And then it says I is less than j, meaning to say it should not be equals to j. So you have to cancel this because I should not equals to j because I is less than j. So j is it's not included. So you have to cancel this one, and this one. So you ended up with this. So I'm not trying to make things complicated, but intuitively it should be the combination of the three. But mathematically, when we want to write the equation, this is how we write it. So we have the sigma, it's a summation where I is less than j. Okay? This is just for your information. We have arrived at the final part of the lecture. This is something that is not new because I have introduced you with the Coulomb's law. So you have to apply Coulomb's law here. So meaning to say, if you have a system which contains two strings, you have a system with two strings. So each string, the length of each string is L. So both strings have the same lengths, L and L. So here I have a positive charge and another positive charge. So I'm assuming that both spheres have the same charge, Q. So here it states that, the diagram here depicts that it is both of them are positive. So they will repel, right? They will repel. At some point, when they repel, the gravity is pulling them downwards, which it will allow the system to be in equilibrium. They are repelling to each other, and then moving this way, away from each other, and the gravity is pulling down, so it's like holding them from moving away up to an equilibrium point. So they will stay like that forever. Okay, they will stay like that forever. So that is the situation here. Do you have any question about the situation here? Do you know the meaning of theta? Theta is the angle between the vertical line and your string. And then A is the opposite of the triangle here. So this is the adjacent, this is the opposite, this is the hypotenuse. So of course, by looking at this triangle, so you have to incorporate sine of theta, cos of theta. Well, this is the trick, no? So the force diagram, you have to use your skill from 101. You have learned this in 101, so the tension of the string and whatnot. So you just apply the same concept to this one, okay? There are many ways of solving this, but this is one of the ways. So I have my string over here. This is the hinge, no? So I have my string over here, and then I have another string over here. So the lengths of both strings are the same. So this is my positive charge, and then my another positive charge. So I have my vertical line here. So, and then I have my A over here. I have A here, and then I have A here as well. If you use Q1, Q2 over 2A to the power of 2 times K. So that is the magnitude. So I'm not considering the sign yet, okay? I'm not sure whether I'm going to use it, so we'll see later. So we have the theta here, we have another theta, because they are in equilibrium, so for sure that the theta here and theta here should be the same. So you have the repulsive force, this is F, this is also F. Let's say if I label this as 1, this is charge number 2, this is F21, this is F12. So I hope you agree with me. So and then I have my gravity over here, mg. So here my g has an arrow just to show you that it is pointing downwards. So I have my tension over here, tension. So not my tension, the tension of the string, okay? So and then I have my vertical component here as the, I have the vertical arrow which represent the tension in y direction. So this is Ty, this is Tx. So I have to put the arrows on top of them. So the force is not, the electric charge is not moving, no? So the net force is 0. If you push my face this direction and then you push, another guy is pushing this direction, the net force is 0. I'm not going to go anywhere, assuming that the two forces are having the same magnitude. Okay? But the thing is, the net force is 0. Nothing has been done. I'm not moving at all. Okay? So the net force is 0. The net force is 0 because it is not moving. If you have a system being pushed in various directions, okay? If you have a system that is being pushed in various directions, but these forces ended up with the body itself not moving, then the net force is 0. Okay? So you can always watch my video recording here again and again just to get the understanding. So meaning to say, the force in this direction should be the same with this direction. So I'm writing this as F21, and then the y component is 0, the x component is F21. So I'm using this kind of notation for vector, okay, instead of using I and j. So bear in mind, okay, I think you have encountered this kind of notation, right? So, and then you add with, you're done with this one, and then you're not done with this guy, with the gravity, okay? So the gravity is in the z direction, mg. So now I don't put any arrow because I'm considering the scalar value of g, 9.81. So this guy is 0 in x component. So and then I add with the tension along the x-axis and the tension along the y-axis should be equals to a 0 vector, not 0, okay, a 0 vector, which means we have 0 and 0 for I and j, 0. So what you need to do, I think this is your homework, okay, this is your homework. So this guy, Tx, is given by, so here theta and theta here should be the same. So I'm going to replace this with the magnitude of the tension, T. Now, T here is a scalar value. So T here is a scalar value. So the the horizontal axis will be, so here should be sine of theta, because if you see here, the component here, I'm not going to repeat this, yeah, because this is what you have learned in 101. So the component of T, the vertical one, is the theta here and theta here are the same. So this one should be sine, T sine theta. And then here should be T cosine of theta. Do you know the reason why? I hope you know the reason why, yeah? Because you have learned this in 101. Please, my students, my lovely students. The sine of theta is given by sine as sine, the opposite O divided by H, L. So here sine of theta is given by the opposite A over L, right? Am I right? Okay, it's OH. And then cosine of theta is given by CAH. So you have to find the adjacent here. So the adjacent here, you can assume this as the triangle. So you have the adjacent as the square root of L squared minus A squared. Are you okay with this? This is Pythagoras theorem, okay? So you have T cosine of theta, cosine is CAH, so it's L squared minus A squared square root over L, like that. So as you can see here, I can divide this into two simultaneous equations. So last but not least, you have to substitute the guy here into here, okay? You have to substitute this guy into this guy. So assume that the charge is Q, so you will have Q squared. Because Q1 is equals to Q, Q2 is equals to Q, so Q1 times Q2 is Q squared, right? Q squared. So the distance between the two charges is given by 2A. But the thing is, in the equation of Coulomb's law, you need to divide by R squared. So you have 2A to the power of 2. So you substitute this guy. So this element should have the variable A. Q is already known, okay? Q is already known. K is also known. We assume that this is happening inside a free space or inside the vacuum. So you have T, the magnitude of the string tension, and then you have the A. So you solve the equation simultaneously, a system of two equations with two variables, t and a, and then finally you've got the answer. You got the value of t, you know the tension now, and then you know the separation distance. So if you have any question, you can ask me. So that concludes our lecture. Bye-bye.